Swayam Prabha. Digital India. Educated India.
In the last class we had looked at pressure fed system. Let's look at turbo pump fed systems in this class. Before we go there, just to refresh the required volume of the tank, this will have to include the volume calculated from propulsive considerations that is if you are looking at what is the mass flow rate from thrust, calculate, knowing ISP, calculate mass flow rate, and then knowing density of the propellants and the burn time, you can calculate volume, right. And in addition to this, there will be some trapped propellant in the pipeline and also in devices. Even in the tank you will not be able to expel out all the propellant, there will be a small fraction of it that will be left unexpelled. So this is that. Then a certain portion of the propellant boils out, that is depending on whether it is a cryogenic, this fraction will be a larger fraction because the ambient temperature is much higher than the propellant temperature. So this boiling will be higher in a cryogenic propellant. And lastly, there is something called ullage volume. Now, if you fill the tank to the brim, there is a problem. If there is boiling, then the pressure tends to build up very rapidly, and the tank may not be designed for a high pressure. If you are particularly if you are looking at a pump fed system, right, because pump fed system, most of the pressurize is given by the pump. So the tank might be able to withstand only a few bar pressure. So if you fill the entire tank with liquid, then the pressure as it boils, the liquid boils, will build up, and therefore that might create a problem. So you give it a small extra space so that the pressure end can also act, right. So this is known as ullage volume. This is typically something like 2.5% of that is volume arrived at from propulsive considerations plus trapped propellant, 2.5% of that. This is some kind of a thumb rule that people use to calculate what should be the ullage volume. Okay. So, this will give us the overall tank volume. Okay. Now, in the earlier case when we were talking of pressure fed systems, what we used to do was we used to have a gas bottle and we tried to size the gas bottle, right. Here what we need to also calculate is what is the pressure that is required at the end of the or after pumping. At the end of the pump, what should be the pressure required? One is we know volume flow rate, the other one is pressure required is to be calculated. Now, from equilibrium calculations, we will know what is the chamber pressure PC, right. So, if we know the chamber pressure, then how do we go about calculating the pressure at the pump exit? Okay. PE indicates pump exit. So, this pressure at the pump exit will be the chamber pressure, right, plus the pressure drop in the injector fine, and then there is pressure drop in the recirculating chamber, right. It is a coolant jacket with very fine tubes. So, there is a large pressure drop in these in this coolant jacket. So, there will be a pressure drop RC is recirculation chamber or regenerative chamber, sorry. Okay. Then in addition to this, there is other pipeline through which there can be pressure loss. So, there is a delta P okay. So, if we know all this, then we can calculate what is the pressure required at the pump exit. Now, this we will be able to calculate from equilibrium considerations. What about this delta P across the injector? We will know the mass flow rate, right, mass flow rate through the injector that is to be given. So, how do we calculate this delta P across the injector? So, if you look closely at the injector will be something like this. This is injector and this is the manifold, and here is the thrust chamber or combustion chamber, right. So, there is a manifold that is upstream of the injector. Now, it is so designed that this area is very small compared to the manifold area, and if that happens, what can we say about the velocity of the liquids? Remember, firstly, most of the fluids that we are dealing with are incompressible liquids in this case. So, if you are having incompressible liquids, then what are the things that you need to consider? Equations of mass conservation and momentum conservation. Momentum conservation in this case, because density is constant, you can use Bernoulli's equation, right. So, let me call this as 1, this point as 2. So, rho 1 A1 V1 must be equal to rho 2 A2 V2, right. This is mass conservation. Then momentum conservation is P1 by rho 1 right. So, now if you look at this term, the square of the velocity in comparison to square of the velocity here, what can we say about it? Because we made the areas in such a way that this is very small compared to this. So, I can neglect this in comparison to this, okay. So, we will get for pressure drop across the injector, you need to calculate the mass flow rate, so you need the velocity V2. So, V2 would be delta P injector would be is equal to P1 minus P2, fine. So, rho is the same anyway, it is an incompressible liquid. So, therefore, this rho 1 and rho 2 do not change. So, you will get that equation. Now, we know the velocity, we need to calculate the mass flow rate. So, mass flow rate is given by m dot is equal to rho AV, right. In this case rho 2 A2 V2, fine. But what can you say about this? This is if the actual area is this one only, but because there is a very narrow constriction through which you are forcing the liquid to go through it, and because of boundary layer effects the actual area will be smaller than this. So, therefore, you need to consider a coefficient of discharge. So, you will have CD into A injector, okay. Now, if I take the rho inside, there is one rho already, right, under the square root. So, you will get under root fine. This is for mass flow through one injector, right. In a rocket motor there are going to be a number of injectors. So, you need to multiply it by n. This is nothing but number of injectors, and CD is coefficient of discharge. Let me also call this as rho L. Okay. So, we know now if you look at this equation, if we know what is the mass flow rate that should go through the injector, we can back calculate what should be the delta P across the injector. Okay. So, then coming back to this equation, we know this, right. Now, how do we calculate this part? Delta P across the injector, regenerative chamber. If you remember, we were doing we had dealt with how to calculate the heat transfer coefficients and other things, right. There, if you know the mass flow rate, and again mass flow rate you will know, so you can use a similar relationship to calculate the pressure drop across the injector. Anyway, the density is going to be the same, areas might change, right, but you can calculate what is the pressure drop across the injector, right, regenerative chamber, fine. So, this part is we can do, and similarly delta P across pipeline is, again you will know the diameters, so you can calculate what is the delta P in the pipeline, fine. So, overall you will get what is the pressure at the exit of the pump that you will be needing. So, we know the mass flow rate of the propellants, we know the pressure at which they need to be delivered. So, what can we calculate? If we know these two things, we can calculate the pump power required, right, and then based on efficiencies we can again calculate what is the turbine power that needs to be given to it. Okay. Yes, if you are using liquid hydrogen, it will be mostly a gas. So, these things will have to take into account compressibility effects. Okay, you will have to take compressible fluids into consideration and rework these numbers, fine. These are for liquids. If you have liquid hydrogen, that is the only case wherein it will become a gas probably. So, you need to rework this for a gas. So, okay. Now, we know what is the exit pressure at the end of pumping that is required, right, we just calculated that. Then what are the other things that we need to calculate turbine power required? The inlet temperature to the turbine is a very critical parameter, right. Turbine, you must have studied this in jet engines or gas turbine engines, that inlet temperature cannot be very high, and usually in this case it is also restricted to something like 1200. Is approximately around 1200 Kelvin. Okay. You might argue it a little differently here. If you remember, gas turbine engines need to run a long duration, they are long haul engines, right, but the turbine that is used here is probably going to be used for a few minutes, not in terms of hours, right. But then therefore you can argue this way that probably you can go in for an increase in the turbine inlet temperature, but in that case you do not want to do something wherein you will jeopardize the mission, right, although it is for a very short time and for a single use, If you remember, gas turbine engines, they have to have number of hours of operation without overhaul, and they will be used multiple times, which is what makes the design and the construction of a gas turbine engine much more challenging than rocket engines. Rocket engines is always going to be one time use, so therefore it is a lot easier to do this than the other one, right. So even with this, we are restricting the turbine inlet temperature to something like 1200 Kelvin, okay. And you can have a number of stages of turbine, right. So across each stage, we can calculate the power output this is by energy consideration. So PT, the pump power, can be written as Cp where this is efficiency. Tp is nothing but turbine inlet temperature, which is why I said we need to know this if we have to calculate the power that can be extracted from the turbine. This is nothing but turbine inlet temperature. Mt is the mass flow rate through the turbine. And this pi t here is nothing but pressure ratio across the turbine stage. Okay. This is what is the power we can extract from the turbine. Okay. Now this must be equal to the pump power, right. So how do we calculate pump power? So you will have something like pump turbine power balance. So PT must be also equal to what is the power that is required to run the two pumps. Remember, if we have a bipropellant system, we will have two pumps, one for fuel, one for oxidizer. So eta mechanical into m dot f Okay. This is the mass flow rate of fuel, this is the mass flow rate of oxidizer, and the equations that we derived here, delta P across the injector, right. This has to be delta P for oxidizer, delta P for fuel. So, it's not that delta P, I am sorry, I will this is nothing but this delta P F is nothing but P at pump exit minus P in fuel tank. Okay. What is the pump exit pressure that we want minus what was the pressure that was there in the tank will give this delta P by density, this will give the head rise, right. And similarly for oxidizer you have let me put a fuel subscript here and an oxidizer subscript here. Simply because the exit pressure of fuel and oxidizer need not be the same, especially if you are only going to take one fluid through the regenerative chambers, right. You are only going to use one of the fluids for regenerative cooling, that one will have to have a higher pump exit pressure. So, these two are not the same, okay. And this eta pump fuel is efficiency of the pump and this is the efficiency of the oxidizer pump. Okay. So, by using this we can now calculate, we will know what is the mass flow rate of the fuel that we need, what is the pressure rise that we will need in the pump. So, we can calculate this part, power that is required by the pump, and if you equate it to the power delivered by the turbine, right, then you can calculate what is the mass flow rate through the turbine that you will need. This will be known to you, turbine inlet temperature, because that is a constraint, and what is the pressure ratio across the turbine will also be known. So, you will be able to calculate what is the mass flow rate through the turbine that will be needed, fine. Now, there are various designs that are possible for arranging this pumps, and sometimes you can do away without the turbine also. We look at a few of these designs that are listed here. There is something called as monopropellant gas generator, bootstrap technique, and then you have an expander cycle, stage combustion cycle, and thrust chamber bleed cycle. Let us look at the individual designs a little more in detail. This is the schematic of monopropellant gas generator. Now, if you look at this, you have a fuel tank and an oxidizer tank which feeds into the pump, and the pump exit of the fuel is given to the regenerative cooling chamber, which moves up the regenerative cooling chamber and then enters the thrust chamber. Okay. Now, the oxidizer, the liquid flows into the oxidizer pump, gets pressurized, okay, and the high pressure oxidizer will flow into the thrust chamber. The turbine is run entirely by a monopropellant system. Okay. That is, you use another liquid monopropellant to run this, that is, you either use hydrazine or hydrogen peroxide, which needs to be again pressurized with a helium gas bottle, and then you will have a pressure regulator, then the monopropellant tank, and then you will have what is known as the gas generator or the combustion chamber for the turbine, right. The temperature at the end of GG will have to be something like 1200 Kelvin, fine. You can also have a solid propellant cartridge to initially start up this system. So, the monopropellant system drives the turbine, which then runs the fuel and oxidizer pump, and the exhaust of the turbine is fed to a separate nozzle. Now, if you remember controlling the rocket motor that we discussed earlier in the course, there we talked about ways in which we can control the orientation of the rocket motor. One of them was through a separate nozzle. So, this is the separate nozzle you will have, and it will be a very small thrust. So, you can use this to control the rocket motor. This is about a monopropellant gas generator. In this case, if you notice, the gas generator is not coupled with either the fuel or the oxidizer. So, it is an independent system, so you can control it a lot better. But on the flip side, it will have excess weight and you will need to carry one more fluid on board, right. So, this has greater control, but it also means that it is going to be a lot more heavier. Then
What was that solid propellant cartridge?
see, that is used to start up the system. Probably monopropellant systems can start on their own, but if you are looking at any other design, okay, you need some initial gas generation to drive the pump, right. If you do not have any fluid going through the turbine, then it will be very difficult to start them. So, you have this so that the turbines are started. In the other system also it is given as a redundant feature. Okay. So, the next technique that is used is something known as bootstrap technique. As opposed to the monopropellant system, here you will use a part of the fuel and oxidizer, okay, to drive this gas generator. So, you have fuel coming in through the fuel tank and the fuel pump and the regenerative cooling jacket, and it will not directly go into the thrust chamber. Okay. It will go to the gas generator, all the fuel will go into the gas generator, a part of the oxidizer will also go to the gas generator. Remember, if you use this fuel and oxidizer combination, and if you use something around let us say you are using liquid oxygen and liquid hydrogen, and if you use somewhere around O/F of 6, in the chamber you are going to get something like 3300 Kelvin, right. But you do not want that in the gas generator, because the turbine inlet temperature we want to restrict it to somewhere around 1200 and not more than that. So therefore what you do is you only use a part of the oxygen, okay, part of the oxidizer is used, the rest of it goes directly into the thrust chamber, only a part of the oxidizer is used, so that it becomes a fuel rich system, okay, and then that drives the turbine, and the exhaust of the turbine is given to a separate nozzle. You also have a small solid propellant cartridge to start this system. This is about bootstrap technique. This is was used in space shuttle main engine and also in the cryogenic upper stage of ISRO, okay, the GSLV cryogenic upper stage engine. This is expander cycle. Now expander cycle you can use only if you have a LOX hydrogen engine, primarily because if you look at hydrogen, hydrogen if you pass it through the regenerative cooling jacket, the temperatures at the end of the cooling after it passes through the cooling jacket will be so high that hydrogen will not be liquid anymore and it will be a gas at high pressure. So if you have a low thrust engine, right, then you can use this and expand it through the turbine, right, and then feed it back into the thrust chamber. So it's just expansion of this heated hydrogen, right, only with hydrogen this can work. The expansion of this heated hydrogen is used to pass through the turbine, and this will give you the required power to run the two pumps, okay. Mind you, this is only for a low thrust system that it is possible. For high thrust systems you will also need to use fuel and oxidizer composition, because if you look at this system and if you look at the equations here, this is very low, Tp is very low, you are trying to make it up with a larger flow rate of hydrogen, okay. This will be the entire flow rate of hydrogen, but still there is a limitation on how much of power you can get, okay. The next cycle is the stage combustion cycle. In this case you have fuel coming through the pump and the regenerative cooling, and all of it goes through to the gas generator, right, and part of the oxidizer comes here, and the other part goes through to the gas generator, right. After combustion here, the products of combustion are directly fed to the thrust chamber. So this is this can give you very high turbine power. So therefore this is typically used in very high thrust and long duration engines, okay. So this is bootstrap technique. This will have a separate nozzle. Stage combustion is fine. Then lastly you have something known as thrust chamber bleed. Here you take a part of the exhaust from the thrust chamber itself, and as it goes through the pipeline from the thrust chamber to the turbine inlet, there will be a long pipeline, and as it goes through it, it will get cooled, and the turbine inlet temperatures probably is going to be higher than what we had set out here as 1200, okay. It will be higher, which would mean that you will only need a very small bleed, okay. You could also look at in some sense you can cool the turbine feed with either the fuel or the oxidizer, so that the temperatures do not exceed some limiting value for the turbine inlet. Okay. So, you can do that and feed it to the turbine, and then this exhaust is given to a separate nozzle, so as to this can be used for controlling the rocket motor. Now, we had learned that how do we balance the turbine and pump power balance. Now, there are various ways in which you can have, or the essentially two designs of pump that you can have. One is axial and the other one is centrifugal. When do you use an axial pump and when do you use a centrifugal pump when you need a very large head. When head is high, you will go in for a centrifugal pump. If mass flow rate is high and head is medium, then you go in for an axial pump. Okay. So, delta H or head is nothing but delta P by rho into G. So, if head required is high, then you go in for a centrifugal pump, but if head required is not so high, whereas your flow rates are very high, then you go for a axial pump. The advantage with an axial pump is it is pretty much amenable to multi-staging, whereas the losses, if you are using the centrifugal pump and if you are having a large number of stages, the losses could be larger because it will have to go through a volute chamber onto the periphery and then again come back to the center. A centrifugal pump, you always have axial inlet and radial outlet, right. So, the flow turning induces a higher amount of losses. Now, let us look at what are the values of head and what are the values of flow rates that are there going to be there in these some of the rocket motors. So, SSME uses liquid oxygen and liquid hydrogen. Cryogenic upper stage is also liquid oxygen and liquid hydrogen. F1 engine, this was the engine that took man to moon. This uses kerosene and LOX. Kerosene is also indicated as RP1, rocket propellant 1. Okay. Then Vikas engine is nitrogen tetroxide and UDMH, unsymmetric dimethyl hydrazine. So, the Q dot in liters per second and then delta H Now, if you look at this table, this flow rate and head of liquid hydrogen, these are very, very high, simply because if you look at the density of liquid hydrogen, it has got a very, very low density of 70 kg per meter cube. So, therefore, if you look at flow rate, even though the mass flow rates will be very small, the flow rate will be very, very high, volumetric flow rate will be very high, and also the head rise that is required will also be very high, simply because head rise is nothing but delta P divided by rho. Because rho is low, you will have a very high head rise. The same is the case for both SSME and CUS, because both of them use liquid hydrogen. In addition to this, the head rise will have to be more for liquid hydrogen, because it is passed through the regenerative cooling chamber. Okay. Now, if you look at LOX and RP1, you will see a substantial difference in the head rise and flow rate. Although this is a much larger thrust, this engine produces a much larger thrust, the head rise that is required for hydrogen is much higher than RP1. That is primarily because of the difference in densities. Okay. And here again the head rise is nearly the same for both kind of both fuel and oxidizer for the Vikas engine. Okay. We will stop here. In the next class look at what implications does this have. If you have a very high head rise, what are the implications that it is going to have, and let us look at that in the next class. Thank you.